So this is the final talk on the subject of time and space complexity. And today I want to talk about recursive code. How do we compute the time and space complexity for recursive code? Now, we have not talked about the recursion as such yet. Neither we have talked about the divide and conquer algorithms. But basically, when you work with the divide and conquer algorithms or in general recursive code, at that point, and this will become more clear what I'm going to do today. But still, I'm going to cover examples today. So let's look in beginning an example, a very simple one. Okay. Suppose that I have to write a factorial function. Okay. It's a very simple example. It's not at all complicated. So what I'll do is, let's say I'm going to write a quick factorial function. So I'm quickly going to write some pseudocode. Suppose my factorial function is called fact1. And let's say this is some iterative code doing factorial function. So what is factorial? I hope everybody is completely aware of what factorial is. So factorial of a number, let's say if I write is represented by an exclamation sign, factorial 5, this means essentially you are doing 1 and you get an answer. So that is factorial. Suppose you have to write a code to compute the factorial. So the one way it can be done is basically you can do a loop. So you can basically have some kind of a, let's say, answer equals to, you can initialize that answer equals to 1, and then you can iterate from basically you can just keep multiplying answer multiplied equals to that I, and in the end you return answer, sorry. So one way to do that is that by writing this kind of a for loop, that basically you have an answer 1, and then you iterate from 1 to n, and then you multiply each number by, as you go along, you multiply that total with I, and that way you keep computing the factorial. So you begin with 1, and then you multiply 2 with 1, then 3, then 4, then 5, like that. Right? That's one way of computing the factorial. The other way of computing factorial can be a recursive code. The recursive code, once again, I've not talked about recursion. So if you're not familiar, then don't worry too much. But recursion is a technique in which you call the function itself from within the function. So suppose that I'm going to call this, let's say, factorial, to keep the name brief. Let's say this is the recursive code now. So factorial. So first I write a base condition. So I'm just quickly going to write if n equals to 0, then something like, let's say, return 1, else return n multiplied by factorial of n minus 1. So that's roughly the code. So how it's going to be look like. So if the n is equals to 0, then you do this. Otherwise, you return the number multiplied by the same function on a smaller input. The smaller input is n minus 1. So the code, if you notice, right now, it might be pretty equal size, but as you go along to more complicated problems, recursive code tend to be more elegant, more beautiful. And it makes more sense as well when you read it versus the iterative code. However, there's a price that we pay in recursion. So let's understand the space and time complexity of both of these pieces of code and what are the advantages and drawback of each approach. So let's take the iterative approach first. So I'm just quickly gonna copy this. Let's take this code now. So suppose you want to compute the time complexity for this code. Okay, the approach remains the same that we have used so far. So first what we'll do is let's calculate. So first what we'll do is we will assume that there is a cost of each operation, and then we essentially how many times that operation is occurring. So there's a cost and then the times that operation is occurring. So this operation will occur once. So let's say the cost for this is C1, this is C2, this is C3, and this is C4. This operation will occur once. This operation will occur n+1 times or n times, whatever. And then this operation will occur n times. And then this operation will occur once. So when you aggregate all of these, then what this becomes is basically this becomes C2 plus C3 of n plus C1 plus C4, essentially an plus b. And that is O of n of time complexity. So that's straightforward. That is, we have done plenty of these examples, so that's not a big deal for us at the moment. And what is the space complexity for this? We are not using any space in this program at the moment. We have just one variable, which is holding the value of the current running total. And only this variable gets new value. So essentially only one unit of constant space that we are using. So the space here is O of 1. So time is O of n and space is O of 1. That's the iterative code. Now let's look at the recursive code. I'm going to quick copy the recursive code here as well. The difficulty with recursive code is how do we calculate the time and space complexity? So let's begin with the same approach. Suppose you were to follow the same approach, cost and times. So when we enter a function, suppose factorial of 2. So this line will be computed how many number of times? There is no loop here. So at this point of time, it looks like this, that let's say this operate once again, C1, C2, C3, C4, let's put the cost. And then this looks like the number of times this will be computed is just 1. This will be also computed 1 time. Because we're going to check if n is equals to 0. If it's not, then just move forward. And then this line will be computed once. And this line will be computed once as well. It is a multiplication. So this function itself, just by because there's no looping structure here, might look like that this is doing work in constant time. Doing the comparison is O1 time. That's fine. Returning is O1 time. That is fine too. This multiplication is O1 time too. That's fine. How? And but what about this guy? This is the dicey element here. From a function of size n, we have called a function of n minus 1 size. Calling a function is constant time, but that function needs to compute as well. So in order to really get the time, we need to compute the time complexity of this guy. So if this is t of n, we need to find out what is this t of n minus 1 to really find out what this n is. Otherwise, so this is basically some t of n minus 1 plus some constant operations. That's what this is. That's why the recursive functions become tricky. Now, this is a very simple example once again. As the examples become more complicated, this will be harder to compute. So what are the approaches that we can use? Okay, let's save this and we'll come back to this in a second. And let's get a new. One approach to solve these problems is to go through the function call stack. Suppose that in the previous example, we had called factorial of 4. If we look at this piece of code here, that if n equals to 0, return 1, else return n multiplied by factorial of n minus 1. So 4 is not equals to 0. That means 4 should return 4 multiplied by factorial of 3. Right? So this function will go through its loop. If n equals to 0, whatever, I'll just write so some line. If n equals to 0, then do this, else finally it comes to 4 multiplied by factorial of 3. Now, before this multiplication can be executed, this guy needs to be computed. So because this guy needs to be computed, this function needs to be called, and the result of that return of this f of 3 would be used in the computing the output. So what we do is, so what computer does is, it puts this in a call stack because it needs to remember that it is going to come back here. It creates a stack and it puts it there. Now, computer goes into evaluating f3. 3 comes out to be 3 multiplied by f of 2. So at this point of time, in order to compute this result, we need f2. So then this instruction goes on the call stack, and you go on to compute 2. So this becomes 2 into f of 1. Once again, we don't know what f of 1 is. So once again, this is put on the call stack. And we go on to compute f of 1. This goes to 1 into f of 0. Now, f of 0 is a trivial case. The trivial case meaning that it can be solved in a single step. How? We have a condition. If n equals to 0, then return 1. So immediately, this guy returns 1 back. So 1 into 1 is equals to 1. Now, where is this 1 supposed to go? So this computer program knows that it has a call stack. It goes here. It fetches this instruction, 2 into f1, the top of the stack. So it takes this 2 and it multiplies it by 1 here. And that 2 into 1 results in 2. Then basically you go to then this entry is popped, essentially deleted. So now this is the stack top. You can assume this is the stack top. So now this is the stack top. At this point of time, actually, let's keep that figure back. I'm sorry. Let's keep that figure back. We go to this 3 into f2. So which is equals to, this is 2 essentially. So this becomes 6. And then 6 into 4 is 24. And that's how you return 24 is the result of this function. So how do we calculate the time and space complexity? There are 2 things that we need to clearly see here. One, while executing the recursive call, there's a chain of events which also create extra memory somewhere in the which uses extra memory. So consider this, that if this was maybe f of 100, then this stack size would be 99 because you would have 99 calls sitting on a stack. So as compared to a for or a while loop or an iterative approach, you are using some extra memory while doing the recursion. Yeah, and we'll come to it. So let's go back to, so this is one way of calculating the time complexity. Let's calculate the time complexity now for this code. So we saw previously, this is an O1 operation. Multiplying 2 numbers is an O1 operation. Actually, let's go from here. This is straightforward. Multiplying this 2 numbers, 1 into 1 is an O1 operation. Now, when you have an O1 operation, you have the value for this. This is also an O1 operation. This is also an O1 operation. And finally, this guy, the top guy, is also an O1 operation, right? Because here you're just multiplying. However, to get this value of 3, we had to go n minus 1 deep levels. So essentially, when you sum all of this, O of 1 plus O of 1 plus O of 1 n times, this yields O of n time. This is, which is pretty straight, which is pretty clear, because if you have 900 here, then there are going to be 100 multiplications in this chain. If you have 1000 here, then you have 1000 multiplications here. So you can see that it's a linear time. Also, you might notice there's a space complexity now as well. So space complexity in this case is O of n. Because if the input size is n, we're going to have n minus 1 items on the stack. This stack will grow to a maximum size of n minus 1, and from there on it will start reducing. So any question before I move forward? All right, so let's go back here. So we compared factorial code, okay? Factorial code, and what we saw was we wrote iterative code and we wrote recursive code. And the time and space complexity for the iterative code was O of n, and the space complexity was O of 1. For recursive code, it's O of n and it's O of n. So this factor pretty much will always be there with recursion. There's extra space whenever we write recursion. Now the question is, why do we use recursion? So recursion, what happens with recursion is basically you're able to write simple code. Simple, I would also add the word elegant code with it. At some point of time when we go into recursion and backtracking, you will notice that there'll be problems on which writing iterative code would be extremely hard. And it will require, like, the code will become pretty messy. And in that situation, recursive code is very simple and very beautifully written. And that is the power of recursion. But the price is that you pay the price with the extra space. So let's go back to the other approach of calculating the time, which is the let me go back to the saved image. Yes, this one. Which is this approach is called solving this by recurrence. Recurrence relationships. Okay, or you can also call substitution. By substitution. So this is another approach of calculating recurrence relation times. This is actually a very good approach to calculate time of many algorithms. What you do is, in a recursive code, when you see this piece of code, what you establish is a bunch of O1s, and then there is the function being called again. You assume what you try to do is you try to establish a relationship of the O running a function with O n input with some n minus k later on here. So you try to express, suppose the running time for factorial of n is tn. let's say Tn says Tn is the running time of this factorial function, then what you try to do is you try to establish a recurrence relation like this. You're going to say the recurrence the time it's going to take is 1 unit if the input is equals to 0. Otherwise, the time is going to be whatever this constant plus factorial of n minus 1. So t of n minus 1. Otherwise, it will take this tn minus 1 time plus some constant time. You can write c when n is greater than 0. So this is the type of recurrence relationship that you write. Now let me clear the screen and write this again. So the recurrence relation once again we wrote was t of n is equals to 1 when n is equals to 0, and when n is greater than 1 we write it as t of n minus 1 plus c, some constant, assume that. Now this t is the running time. It should be some O of n or something. So in this case this c doesn't matter. What we, for simplifying, we just write it as 1. You can keep it as c as well, it doesn't matter. So what I'm going to do is I'm just going to get rid of this and just write that so essentially what I'm trying to say is for any n greater than 1, the running time of this function is some constant time plus t of n minus 1. Right. So now we come to calculating the time and space complexity, time complexity for this code. So we write what Tn equals to t of n minus 1 plus 1. That's our recurrence relationship. And now what we'll do is we'll use the method of substitution to calculate the time complexity. So what will Tn minus 1 be? If we try to compute this, Tn minus 1 be similar relationship will follow. It will be t of n minus 2 plus 1. So we substitute that here, and this becomes t of n minus 2 plus 1 plus 1, which is 2. 1 plus 1, 2. When you go on computing, it just becomes t of n minus 3 plus 3. Then you go on. At some point of time, this is going to become t of n minus k plus k. If we keep going further, for some k, n will become, this whole n minus k will become 0, right? N minus k at some point of time is going to become 0. At that point of time, k will be n. So when you substitute k equals to n, this becomes t of 0 plus n. Now t of 0 is trivial. We know that for n equals to 0, it's 1. Right? So this becomes something like 1 plus n. Or if you're using constants, then it becomes some c plus n. But essentially, the Tn is equals to n plus 1, which if you go by the asymptotic analysis, this becomes O of n. This is the higher order term. We can ignore all the lower order terms. So that's the method of recurrence relationships and substitution to calculate time. So we calculated the time in this example using two approaches. One is we went through the function stack and we actually computed all the number of operations it's going to take. And this is fundamentally a different way. We express the time of a bigger unit in terms of time of a smaller unit. And then with this relationship, we reduce it down to a base case that gives us an answer.
Himanshu, can you repeat that t of n minus 1 plus n greater than 1? Can you just elaborate there?
Which step are you referring to?
The initial function, you have the t of n equal to 1 for n equal to 0. Yeah, that's the one just now.
So basically,
how did you arrive to that?
So I arrived to that with the code. So let me open this previous file. When you're writing factorial n here, So this is basically if n equals to 0, that's an O1 operation. Return this is O1 operation, else is an O1 operation. But here it calls n into factorial of n minus 1. So if Tn is the time taken to compute this, then Tn minus 1 is time taken to compute this, right? So we can write Tn equals to Tn minus 1 plus all this constant time, all these operations, correct?
Yeah.
So then we can write Tn equals to Tn minus 1 plus that constant time, this guy, which can be written as 1.
Okay, good.
Any other questions? Okay, I'm going to compute one more recurrence relation. So let's look at another example, a very classic, basic example, CS 101 example of recursion, which is Fibonacci. So Fibonacci numbers, right? Fibonacci numbers, what happens is they begin with this. So Fibonacci is a series which begins with 0, 1, and then each number is the sum of the previous two digits. So the next number is 1, then the next number is 2, then the next number is 3, then it's 5, then it's 8, then it's 13. So this is Fibonacci series. Fibonacci series has an incredible growing power. I mean, this grows really fast. So suppose we were asked to compute the code Fibonacci. We were asked to write code to compute Fibonacci. Just give me 1 second. Suppose you're asked to compute the Fibonacci of n, let's say 5. Then essentially what we will have to do is we'll have to write 0 plus 1 plus 1 plus 2 plus 3. That'd be Fibonacci of 5. So if you were to compute this, how would we write the code? Once again, there can be an iterative code. Very simple iterative code is present. You can just loop and loop from 0. So you loop 5 times, and then you begin with 0 and 1, and then you keep adding the running total. But I'm going to go to the recursive code because we are talking about recursion here. So the recursive code can be something like this.
So Himanshu, one question. Fibonacci of 5 means 5th position or starting till 5th?
Fibonacci of 5 would mean Fibonacci of 5th position. So suppose if I say Fibonacci of 1, that would be 1. Fibonacci of 2 would be, so Fibonacci series goes like this: 0, 1, 2, 3. Actually, let me just check. Fibonacci of 1 is 0 or 1. Let me just quickly check. I think it should be 0. Fibonacci of 1 is, let me check. Let's assume right now for our example that this is position, okay? And you have this Fibonacci of 0 equals to 0, 1 equals to 1, 2 equals to 2, Fibonacci of 3 equals to 3, and then Fibonacci of 4 equals to 5, Fibonacci of 5 equals to 8. It goes like that. Okay, so this is the position. This is like the array index. So I'm going with that assumption at the moment. Let's begin. So what I'm just quickly going to write is, let's say Fibonacci of n. Let me just create more buffer here. So I'm just quickly going to write code. So basically, if the base case is there, if n equals to 0 or n equals to 1, then basically return n. That is 0 or 1 belongs to 0. Else basically return Fibonacci of n minus 1. plus Fibonacci of n minus 2. So that's the recursive code. Now you can already start seeing how the code is becoming more and more elegant. Now we are able to express this simple logic that Fibonacci of n is equals to whatever the Fibonacci of n minus 1 and n minus 2 is. So this is the recursive code. This is the base condition for that recursion. So let's compute the time and space complexity for this code. So we begin computing by, we need to compute Fibonacci of this. So let's call this a Tn. Yeah, let's compute by actually both the approaches, the recurrence relationships and the actual call stack. So let's first do the recurrence relationship in this case. So suppose this is Tn. Then how many times this operation is going to occur? So once again, this is cost and this is times. How many times will this be there? One. So this cost is C1 one time, cost is C2 one time, maybe cost of C3 one time, and cost C4. Now here's the real tricky part. How many times will this occur? We don't know that. As far as this function is concerned, it will be occurring one time. But calling this would result in two different set of Fibonacci functions. And then we'll have to compute those as well in order to get the real time. If this is Tn, then basically this would be T of n minus 1. Fibonacci of n is Tn, then Fibonacci of n minus 1 is Tn minus 1. Fibonacci of n minus 2 would be Tn minus 2. Then plus is a trivial operation here. Once you have the numbers, you can easily sum those numbers. So this function Tn can be expressed as a constant time if n is equals to 0 or n equals to 1. Or you can write n is less than equals to 1. And once again, when we calculate this, we don't have to be that explicit. We can just write n equals to 1 or 0, whatever you want. Otherwise, this is going to be T of n minus 1 plus T of n minus 2 plus some k, or you can write just as 1, whatever. And for n is greater than 1. So if this is the case, then can we compute the T of n? So let's go into computing this. So what we have written is T of n. 1 and T of n minus 1 plus T of n minus 2 for n greater than 1, for n equals to 1. So when we write this function, we can plus 1, there's some plus 1 as well, some constant time basically. Now, if we want to compute this, we can simplify this a bit further, okay? And assume this, that Fibonacci of five and Fibonacci of 4. Suppose I want to compute Fibonacci of 6, then that would mean Fibonacci of 5 plus Fibonacci of 4, right? If Fibonacci of 4 takes t time, t running time, then this can be some t plus delta t, right? So Fibonacci of 5 will take slightly more than Fibonacci of 4. If we consider the worst case scenario where Fibonacci of 4 takes the same time as Fibonacci of 5, then we can express the relationship a little simply here by writing n minus 2 equals to n minus 1, right? Which will give us a lower bound. So this can be written as 2t of n minus 1 plus 1 for n is greater than 1. because once again, we can do that because we assume Fibonacci of 4 is going to take same time as Fibonacci of 5. Fibonacci 5 is going to take more time anyway. So we will have an upper bound on time. That Fibonacci function will not cross that upper bound. So if I now solve this recursion, it will be like this. So what would be T of n minus 1? T of n minus 1 would be T of n minus 2, twice of that, plus 1, 2 plus 1. So I replace the T of n minus 1 here with this expression, and then rest of the expression are same. Right? So this becomes 2 to the power T of n minus 2 plus 2. Then n minus 3 will become 2 cube T of n minus 3 plus 3. At some point of time, okay, I'm running out of the real estate here. This will become 2 to the power of k T of n minus k plus k. I'm going a little slow so you guys can follow here. And at some point of time, k will become n, and this will become 0. So n minus k equals to 0 when k equals to n, or whatever, 1, however you want. That's completely okay. So at that point of time, when this becomes k becomes n, this will become 2 to the power of T of 0 plus n. And T of 0 is 1 time. So this becomes 2 to the power n plus n. Tn equals to that. So what would that give me? Tn equals to what? Anybody?
2 power n.
So this is O of 2 to the power n. Any questions how we are computing about how we computing the recurrence relationships here in this particular case? Let's try to understand it from a different perspective, which might be easier for some people. And this is one approach, that is another approach, by actually going through the call stack of the function. So suppose that this is the function, right? Suppose that we want to compute Fibonacci of, I don't know if I have the enough screen area, but let's begin with Fibonacci of, let's say, 4. In order to compute the Fibonacci of 4, our code will go here. It will check this condition, some constant time. Then it will check this guy, some constant time. Oh, sorry, this will only happen once. Sorry, my mistake. Then I'm going to go to else and return these two guys. So in order to compute Fibonacci of 4, we need to compute Fibonacci of 3 and then compute the Fibonacci of 2. In order to compute Fibonacci of 3, I need to compute Fibonacci of 2, then Fibonacci of 1. Then in order to compute Fibonacci of 2, I need to compute Fibonacci of 1, Fibonacci of 0. Similarly, here Fibonacci of 1, Fibonacci of 0. So for input of 4, how many times this function is called? Right? This can be represented as, this is like a binary tree, right? Where this is, each node here is forking 2 different child. So for each node, there are 2 child. And each child is taking constant time to do the work because, as I mentioned previously in a previous diagram, how inside the function this constant time. So if this is taking, so if this is 1, then basically this is 2 times. This is 2 to the power 2 times, which is 4. And we go on like this. It's not a perfect binary tree, but we can assume the worst case scenario and assume that, okay, everybody has this. It's on the same level. That's the worst case scenario to get the upper bound. Then this will be some 2 to the power k if we keep going further. If this was 2 to the power 5, then we'd have gone down further. Now, the question is, what would be the depth of this tree? If this is 4, then the depth of the tree is 3, 2, 1. It is reducing by 1. So the depth of the tree is n. So this whole height of the tree is n. So this is k equals to n. So this is 2 to the power n. So at base, there are going to be 2 to the power n leaves. That gives us the time complexity of 2 to the power n. Any questions?
You're sharing in every problem 2 different way of actually finding this complexity.
Yes.
But which one we need to use like in most of the problem, because both us having a different approach. And how do we know, like in the previous problem you have mentioned we need to replace the t value, but in the factorial problem you have not replaced with the t value. And how do we know all those, like where we need to replace or when we don't need to, or like in this, like
In
which
the
one?
in the factorial value, in the factorial as well, we replaced, right? So let me. So in the factorial case, we wrote this, something like t of n equals to t of n minus 1 plus 1, right?
Yeah.
Then we replace this n minus 1 with n minus 2 plus 1
Yes.
plus 1, right? So replacement was there.
Okay, yeah.
Then t of n minus 3 plus 1 plus 1 plus 1.
Yeah.
That's how t of 0 plus n, and hence this is 1 plus n. So both the approaches are equal approaches. It's completely up to you. So consider this, for example, there are different approaches of a way of approaching the same situation. Suppose I'm going to give a different analogy. Okay, suppose that this is, for example, in physics, right? Let's say this is height of this roof and you drop a ball from here, right? Then what would be this velocity of the ball when it reaches at the bottom, right? You can do this in multiple ways, right? You can use the Newton's law of equations like v equals to, the law of motion like v of u plus at, which is 0 plus g into whatever t, and then you can do that. Oh, sorry, this is not a good algorithm. So something v square equals to u square plus 2ax to solve this problem. Another way can be to compute the energy. So mgh equals to half mv square. And then height is known and you can calculate the velocity. So both will give you the same answer if you compute these two. It's the same. And so I've given an analogy here, but it once again, though in recurrence relationship, there's one way is to actually compute the number of times, as we always do, number of operations, as we always do. And then there's another is calculating the recurrences. This is expressing Tn equals to some T of n minus k. Both are equal approaches. It's whatever you're comfortable with. You can use that. Okay. More or less, I think I have found what people use the other approach more. So for example, people use this approach more.
Okay.
People use this clearly draw this binary tree, and then they compute how many leaves are there, how is it growing, and then what is the depth of it, and then you get the answer.
Thank you.
But once again, as I mentioned in the beginning of the class, we have not talked about recursion yet. We have not solved really problems of recursion. As we go forward, this will become more and more clear, and then you'll get an idea as you solve more recursive problems. Any other question? Okay. So what I'm going to do is I'm going to end this session here at this point, because I think whatever I wanted to cover in the time and space complexity, I've covered it. If you have any question, you can stay back and ask any question. Now, in the next follow-up series from here onwards, I'm just quickly discuss. I'm going to talk about. I'm going to begin talking about arrays and strings, followed by stacks, queues, and linked lists. Then recursion and backtracking. So this is going to take some time. So this would be, I think 2 lectures roughly. This should be 3 to 4 lectures. I'm taking the upper bound 4, and this will be another 4. So this is some 1.5 month worth of material.
So Himanshu, this is for time and space complexity, or the problems and solutions as well?
What do you mean by that?
I mean, with arrays and strings, you are going to discuss